Hello, so in this video we'll talk about Euler's paths and circuits. So let's start again with the definition. So we have some equivalent statements about the Euler circuit. So for example, if we are told that each vertex of a graph has an even in degree, or if it is a directed graph, then the equivalent statement is the in degree of each vertex equals the out degree of that vertex. For each vertex, in degree equals out degree. Or we are told that each edge in the graph belongs to an odd number of circuits, or we are told that a circuit exists in the graph that passes through each edge exactly once, which means a simple circuit, and each vertex at least once. So these are all the equivalent definitions of Euler's circuit. So I mean, in textbooks, this the third statement is usually referred to as Euler's circuit. Okay, but for the sake of understanding, all these three statements are equal. Okay, similarly, for if we have Euler's circuit, we have these equivalent statements. For we have Euler's path, we have these two equivalent statements. So let's read the second one first. It says a path exists in the graph that passes through each edge exactly once and each vertex at least once. And if since it's a path and it's a circuit, so circuit by definition starts and ends at the same vertex. So this means starting and ending vertices are different. Okay, so this is just by definition. I mean, we don't have to write it, but this is just by definition that this distinguishes this Euler's circuit from Euler's path. Okay, so in this case we have this even degree for Euler's circuit, but for Euler's path we have to have even degrees for all of the vertices except two of them, exactly two of them. But for a directed graph, what we have want to see is that a vertex exists whose in degree is one more than its out degree, and there is one vertex with in degree one less than its out degree. So there should be all the vertices have should have in their in degree equal to their out degree except two of them. One of those two has in degree one more than the out degree, and the other one should have out degree one more than the in degree. Okay, so this is the condition for not a condition. If this is known, then this is also, this comes from that and this comes from that. So these are equivalent statements here. So just as a side note, some applications. So for example, the Chinese postman problem, it says that if a postman has to travel each street of a town, and he has to travel each street once, so how does he should plan his path? So this is actually in other words, we want to find a Euler's path or Euler's circuit for that town. And then there is an application in sequencing of DNA in molecular biology. Okay, but these are just side notes of that this is useful in many different areas. Okay, now we come to how to construct an Euler's path or circuit. Okay, so let's say we have this example in which the vertices are labeled as A, B, C, D, E, and the edges are labeled as E1 to E11. Okay, so first of all, what we want to see is we want to see whether it, you know, whether one of these conditions are true or not. Okay, so first let's write the degree sequence of this. So degree sequence of degree of A is 4, degree of B is also 4, degree of C is also 4, degree of D is 1, 2, 3, 4 again, and degree of E is 6. Okay, so all of them have even degree, right? So this means there is a circuit that exists. Okay, so first of all, in this part we will do it through inspection. So let's start with A. So we have A, then we go to E1, then we go to E, then we go to E2, we go to back to A. Okay, then we go to E3, then we go to E again. Okay, then we go to E7, then we go to C, then we go to E10, then we go to D, then we go to E11, then we go to C again, then we go to E9, then we go to B. From B we can go to E8, then we go to D, okay, and then we can go to E6, then we go to E, then we go to E5, then we go to B again, then we go to E4, then we go to A again. Okay, so then we have how many edges we have checked? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And each vertex we have covered. Okay, so we have traversed all edges, and we started with A and we ended with A. So this is one Euler's circuit for this graph. Okay, but now you have noted that this is a very, this is a method by inspection. But by the way, this inspection method actually works if you can see the graph and it's a small graph, and you can, just look at it and draw, do this. But you can also appreciate that if we have a big graph with many edges and many vertices, then it would be very long for a human mind to do it. So it's good to have a, you know algorithm. So let us look at one such algorithm, which is called the Fleury's algorithm. So the algorithm goes like this: we choose edge successively and remove the edge once we choose it. Okay, and the next edge should begin where the last edge ends, and we should avoid cut edge unless there is no other choice. Okay, so let's start with I'm going to do only right edges here, because it's a once we write the edges, the vertices will be automatically defined. Okay, so first of all we'll start with writing edges, so we'll say E1, then we remove this E1. So what are the adjacent choices for E1? We have E2, or we have E3, or we have E4, or we have E6, or we have E7. So let's choose E2 here. And similarly, next choose E3 here. Then next choose E7 here. Okay. So let's see. We have chosen E2, we have chosen E3, and we have chosen E7. So now let's see how does our graph look like. So we have our A to B to D. This is still intact, and 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 this is still intact. Okay. All of them are gone. Now let's choose for E7. We can choose E10, E11, E9, or E6. Okay, so let's choose E10 here. Now E10 is also gone. Okay, now I will choose E11. So E11 is also gone. Okay, now let's see how does our graph look like. So our graph will have this gone, this gone, this gone, this gone. Okay, now let's choose E9 and let's choose E8. Okay, so E9 is our this guy and E8 is our this guy. So now this is also gone and this is also gone. Okay, so this vertex is still here. Okay, so after E9 and E8 we can choose E6, E5, or E4. Okay, but we should avoid choosing E4. Why? Because we have to end up at A. Okay, we started with this one. Okay, so let's choose, we are here, so we were here. Okay, so we choose this E6. So this is now gone, then this is now gone, and this is now gone. Okay, now you can write the vertices if you like. So E1 is between A and B. We started with A, right? So E1 is from A to E. So E1 is from A to E. E2 from E is again A. E3 from A is again E. E7 from E is C. E10 from C is D. E11 from D is C. E9 from C is B. E8 from B is D. E6 from D is E. E5 from E is B, and E4 from B is A. Okay, so this is actually the same path which we did by inspection here. Okay, but this is a algorithm which you can write it a code for if you have a graph in terms of their set of vertices and set of edges defined by the pair of vertices. Okay, then you can write a code for Fleury's algorithm. Okay, so this is a small introduction about the Euler's path and circuits, and how we can use a systematic algorithm to find an Euler's path. Note that this is not the only algorithm. So this is one of the algorithms, and the purpose was to make us appreciate that if we have a big graph, then we should have a sequence of steps so that we can feed into the computer and we can find a Euler's path or circuit for a given graph. Okay, so this is it for this video. I hope it was easy to understand. Thanks for watching. Hope you liked the video.